Hi sir, I'm Kugan from Group E and we are here to present our presentation slides for assignment 2, which is an image classification project with supervised machine learning. Our group consists of 4 of us, starting with the leader, Awan, followed by Sridharan, Tarvin, and me, Kugan. So today we'll cover the project's problem statement, objectives, and network architecture, which includes the workflow of the codes and its outputs. I will be presenting the problem statement, objectives, data preparation, and pre-processing together with the training of machine learning. Followed by Sridharan, who will be presenting the machine learning evaluation and training of deep learning. Then Tarvin, who will be presenting the evaluation of the methods. Lastly, Awan will be presenting the live facial detection codes with a demonstration video and concluding the presentation. So let's get on with the presentation. Firstly, the problem statement. As given in the instructions, Dr. Joel is concerned with the student's emotional health and wants an AI solution to detect the facial emotions of students. Hence, the first challenge is emotion recognition of students to identify their emotional health based on the facial emotions. Next, the requirement of real-time processing so that the program can monitor their live emotions and update them regularly to the system. Furthermore, we must overcome the limitations to adapt to various lighting conditions, facial structures, and demographics. Although there are various open source codes available in the internet, the team wants to obtain higher accuracy in identifying the emotions of the user. Next, we move on with the objectives of the project, which are derived from the problem statement. First and foremost, classifying the emotions accurately based on the user's facial pattern is important as that is the core of the project to detect the facial emotion of the user based on the training model and test model. Next, implementation of live feed camera for real-time processing of the facial detection is also important as it regularly updates the user's emotion to the system. Furthermore, the implementation should be able to adapt to various environments to increase the prediction accuracy as stated in the problem statement earlier. Moving on with the network architecture, I will start with the data preparation and pre-processing. So, as you can see in the codes here, both deep learning and machine learning has similar data preparation methods, but deep learning has extra steps to ensure the model is trained properly. And moving on to the slide. So, firstly, we source the data set from Kaggle.com. As you can see here, there are 7 emotions, but we only chose happy, sad, and surprise. So you can see happy has 7,000 files, sad has 4,900 files, and surprise has 3,200 files. It is an uneven data set, so we have to balance it in the codes later on. Then we import the libraries and specify directories for the program to access the images. After that, the number of images are limited to 2,000 in deep learning and then 1,000 in machine learning. This is done to provide a balanced data set between the happy, sad, surprise emotions. Since the data set from Kaggle is uneven as shown earlier, so it is better to train the model with a balanced data set. Then the data pre-processing phase starts with creating a training data set that can be seen in the codes here. Then the resizing images occurs and converting them to grayscale. But in this data set, it is already in grayscale. So to ensure the model takes in a variety of images, the data is shuffled. The training data is shuffled in random, and the first 10 samples are printed. It can be seen here. After that, the features, which is the x variable, and the labels, which is the y variable, are converted into NumPy array, and the values are printed over here in the output. All right. Once we have processed the data from machine learning, we move on to the machine learning training part. The machine learning training starts by splitting the training and test that into 80 to 20 ratio that can be seen here and implementing the random forest classifier with 100 decision trees as more trees can lead to improvement of performance. Then you can see the output of the implementation below. The process continues by testing the classifier performance to check whether the RFP have been implemented accurately or not. So the program initializes a list to store the prediction value. Then it extracts sample images from 20 to 35 images to test the set. Then we use a for loop to iterate through the images and append the prediction value into this list. Then the string labels are set accordingly. So if it's sad, it is 1. If it's happy, it's 0. If it's surprised, it's at 2. And then the images are shown in grayscale according to the emotion labels. So from the output, you can see the images are shown in the output with the respective emotion label. However, it is not entirely accurate. As you can see here, this image is happy and it is showing sad, but it can be further improved with more training and wider range of images. Next, I'll pass on to Sridharan to talk about the machine learning evaluation. Thank you.
Okay, thank you, Vivian. So now moving on to the deep learning model training. So first the data set will be split into a training set and validation set. And before training the model, we will first use several configurations to compile the model first. So they have a close look at those codes. So once the training set and validation set is split into a ratio of 80 and 20 using the test size of 0.2 over here. Convolutional layers are used, three convolutional layers with kernel size of 3 by 3. 128.256 and 512 is used to detect the complex features of the data set first. And then the flattened layer is applied to the output. And then a dense layer of 256 is first used before using a dense layer of 3 to detect to have a multi-pass detection, which is like happy, sad, and surprise. So we are having a dense layer of 3. And then a softmax is used for activation since it's a multi-class detection. So to compile the model, first the sparse categorical cross entropy is used. Since the dataset is having a p classes, so we're using sparse categorical cross entropy. Optimizer, we're using the optimizer over here, the Adam optimizer with a learning rate of 0.001%. And then the metrics will be our accuracy over here. And then this is the model summary, which is generated using the model summary command. And then once this is done, the early stopping feature is implemented to make sure the validation accuracy doesn't reduce a lot for the patients of 5. And then the best way to be restored if this happens. And then once the model is trained, it will be saved as model trained CNN. So in our codes over here, the early stopping feature is used. And then once this is done, the model is then trained using the training set, the validation set, using an epoch value of 100, batch size of 32, and then using the early stopping feature. And then the training set will be saved as model trained CNN. So as you can see here, once we started training the data, training the model, the validation accuracy actually gradually increased from 0.3 up to 0.7, and then it went up to 0.7867, and then there was no further improvement in the validation accuracy for 5 iterations, so it stopped halfway in 64 epochs. Then the test accuracy is 0.79, which is actually quite okay for this model, and then it is safe. So to test the train model, we first use several codes to test the probability values, and then use 15 images to check if the emotion detection is working correctly or not. So as you can see here, once the model is done training, the model is then used to detect the probability. So this is the probability array with 0, 1, and 2. So 0 is happy, 1 is sad, and 2 is surprised. And then the probability value is checked if it is above 0.7 for each of these attributes to see which is happy, sad, and surprised. So these are the 15 images shown here. So to demonstrate, this is the first image. So this is sad, right? So this is because in the probability array, 1 over here has 0.9, while 2 and 0 has a value lesser than 0.7, which is quite low. So hence, the first image is depicted as sad. So this logic follows for the rest of the 14 images over here. Right. So now I move on to demonstrate the live emotion detection algorithm using this trained model. Okay, so now moving on to the live face emotion detection algorithm using the trained deep learning model previously. So this is the output of the trained model. So when I'm sad, it shows sad. When I'm happy, it shows happy. And when I'm surprised, it shows surprised. But there were still certain fluctuations in this detection, but this is the output image over here. So to have a close look at those codes, first, the Husky frontal face default XML file is used to detect the face, detect my face, person's face. So the trained model is imported over here, and then the emotion labels are set over here, which is happy, sad, surprise. And then the video is captured using my webcam, my laptop webcam. And then the image detected by my laptop webcam using OpenCV is first processed. And then once this is done, the prediction takes place where it predicts if the image over here is 0, 1, or 2. So 0 is happy, 1 is sad, and 2 is surprised. And then this is then displayed in a small yellow box in the output, which is happy, sad, or surprised. Right. So we give this code a run. Okay. So you can see here now it thinks my face is sad, then happy, then surprise. So as you can see, there is still certain fluctuations in the image detection. So this can be because the training accuracy might not be enough for this model. So further improvement can be done to the detection algorithm. So but for now, yeah, it's a bit all on and off, right? So yeah, so uh, that is for the demonstration of the live patient detection algorithm. Okay, so I'll pass the floor to Darwin to explain more about the model evaluations. Thank you.
Thank you, Sridharan. Hi, sir. My name is Talvin, and I will be presenting on the evaluation of machine learning and deep learning. Initially, for the evaluation, we intended to use a random forest classifier to predict classes on a test dataset as shown here. The resulting classifier report shows us the model's performance, showing precision, recall, and F1 score for each class 0 for happy, 1 for sad, and 2 for surprise, along with our overall accuracy. And the confusion matrix further details this classification display the results. The models achieved an overall of 61% with varying precision recall values for different classes. After the confusion matrix evaluation, we wanted to utilize scikit-learn to generate a display receiver operating characteristic, which is ROC curve, for a random forest classifier in a multi-class classification scenario. This classifier is trained on data split into training and testing set, and the code calculates the area under the curve, which is AUC, for each class. So representing the model's ability to distinguish between different classes as shown in the code, the resulting AUC value of 0.97 for class 0 and 0.95 for class 1 and 0.96 for class 2 indicate the excellent discriminatory performance with values close to 1, distinguish strong model capabilities in the distinguish true positive, true negative for each class. However, the ROC curve of class 0 happy is the best performing out of all of them. Moving on to the deep learning evaluation. Deep learning. After training, the model's performance is evaluated on the validation set, and the test accuracy resulted in 0.795, which is almost about 80% of accuracy. After the training, the matplot library was used to create a plot to show the training loss over the epochs during the deep learning model's training process. The plot is important to assess the model's convergence and to identify the potential issues such as overfitting and underfitting during the training process. This plot also shows us when the epochs increases, the training loss decreases. After that, we went on to use the matplotlib library again to create a line plot to show the training accuracy and validation accuracy of deep learning models over different epochs during the training process. The training accuracy curve was plotted in blue as shown, and the validation accuracy curve is plotted in orange, where when the epochs increases in this graph, we can observe both the graph accuracy increases. And we went on to also create a confusion matrix and a classification report for the classifiers. And based on the results, we can see on the predicted confusion matrix, we can see it's 0.7, 0.46, and 0.9, which indicates that class 0 has about 70% of its prediction correct, and class 1 has about 46% of its prediction correct, and class 2 has the most, which is 90% of its prediction were correct. After that, we wrote this code to create a ROC curve. This code visually represent the performance of a multi-class classification model by plotting the ROC curve for each class and calculating the area under the curve as a summary metric. The ROC curve helps us assess the trade-off between the true positive rate and false positive rate at different classification threshold, where a higher AUC generally indicates a better performance. So based on that, class 0 has the highest AUC, which is 0.79, which indicates that the class 0, which is the emotion happy, has the best performing part of the training session. That's all from me today. Thank you.
Okay, so in conclusion, the confusion matrices, classification reports, and ROC curves were all used to assess both of the model's performance. So the RFC model achieved a total of 86% average accuracy and AUC values ranging from 0.95 to 0.97. So this actually shows that the RFC model is actually performing quite well. And followingly, the CNN model is actually demonstrating a slightly lower average accuracy of 77%. So comparing both of these models, it could be observed that both of these models exhibited challenges in identifying the surprise emotion accurately. So this may be because RFC is more preferred for smaller scale problems, providing simplicity without any extensive use of GPU training. CNN model has the potential to actually be used for more complex problems such as multi-class identification. More than happy, sad, surprise, it could be used for angry, fear, or any more emotions additionally, right? With some improvements in the parameters and so on. So the CNN model was used for our real-time facial emotion detection algorithm, and the CNN models were successfully extended for our live facial detection algorithm using a live video feed from our laptop webcam. And considering the results, the output given from the live detection algorithm the fluctuations of the happy, sad, and surprise. No, it was not very consistent, but it could differentiate at times when the face is sad, happy, and surprised. So more potential improvements can be done to the CNN model, and the parameters can be further fine-tuned to improve the average accuracy. And these challenges faced by the emotion detection algorithm can be addressed in the future to improve the algorithm further on and make sure the detection is more accurate and more consistent. So that's our demonstration video. Thank you for watching.